All right, good morning, everyone. Morning. Let's get started. Welcome to EECS 151 lecture 19. I hope everyone enjoyed the guest lecture last Thursday. Now we're going to be back on track. We're going to wrap up wires today. We're going to talk about energy and then start talking about arithmetic. But first, let's recall what we were talking about last week. Please go ahead and take a look at this warm-up and give it a try on your own for the next few minutes.
Oh, good. Each, yeah, each. Oh, this is where, yeah. I'm sorry, but why is yours on each thing?
Let's take 30 more seconds to wrap this up.
Whatever he's done, so it doesn't have this. Even in research here, but once you get to number nine.
All right, let's talk about this one. I see some folks are done and some folks are still working. That is okay. So last Tuesday we started talking about wires as a very important and previously neglected component of our delay analysis, which mostly focused on logic gates until then. And to calculate wires, we had this very simple pi model with R's and C's. And we introduced this concept of Elmore delay. So we're trying to figure out the delay from A to Z in this problem statement. And so we're going to do this tree walking or path walking method, right, to figure that out, to find our time constant tau. I don't know about you all. every time I draw a tau, I really want to draw the little tail going the other way. So I'm trying to concentrate really hard and make sure I draw them the right way, but if I get it wrong, I apologize. Okay, so let's practice our tree walking on this warm-up here. Right? Recall that we start with tau of 0, and then we add to it for each step along the tree, each step along the path. Every time we get to a resistor, we need to look at all the capacitance downstream of that resistor. So we'll walk along here. Okay, we found our first resistor. And so this step of the delay has a time constant of R times all of the downstream capacitance. So can someone remind us what we mean by downstream capacitance? A little more precise definition? Well, let's try this example first. So what is the downstream capacitance from this first node? Yes. Can you explain how you counted that up?
Talked about last time, all potential paths for space.
Mm-hmm.
So there are a few capacitors. I guess 1, 2, and then there's 2 different capacitors from the inverter there. So that's 4, 5, 6, 8, 10, 9 from both paths.
Yeah. So, right. So we talked about capacitance as all of the places that current can flow downstream of that node. And I do count 9C on this diagram. But let's be a little careful. Remember, if you look inside an inverter, looks like this, right? Oops. So can current flow through an inverter from the input to the output node? Right, the gates of a transistor don't conduct current. They just are a capacitance. So you have to keep in mind that when you have current flowing at the input node, this is the end of the line. It's going to hit these gates and then stop. And then the current at the output node is drawn from VDD or sunk to ground. So this is a little bit different than what we looked at in the previous example in the previous lecture, because current cannot flow from the input to the output of these inverters. And so these capacitances at the end are not actually downstream according to our MR delay definition. A little tricky. Are folks feeling, does that explanation sit well with you? Right, this is one of the nice things about CMOS and about transistors is that current doesn't flow through them, right? We have these restoring paths, but it means that anytime you hit a logic gate, that's the end of the line for a more delay calculation. So this downstream cap of the first stage is just 7C, right? These 3 capacitors in front plus the 2 inverters. And then we'll keep walking along our tree. We hit another resistor here. Now downstream of this, there's just this remaining capacitor plus the 1 inverter. So we get R times 3C. And so 10RC is our final time constant when we get to node Z. Any questions about it? Yeah, it's a little new, I think, but not too complicated once you get the hang of it. You'll have some more practice on your homework this week. Yes, question here. Yeah, you could, right? Because, and I won't go through it here, but as you know, we've modeled the inverter as just its own resistor pulling down plus a capacitor, or a resistor pulling up plus a capacitor. And so you can actually do the analysis of logic gates themselves using Elmore delay. You have to do it in two stages though, right? Because again, the current is not flowing through the inverter. So you would analyze delay from A to Z, and then you would analyze delay, from the output of the inverter to the final node and sum them to get the total delay. Yeah, so oops. Let me redraw the transistor here, but using our switch model, right? So, right, so calculating in this example, the delay from A to Z, well, Z is at this node, right? So that gets you as far as the inputs of the inverter. And then for the purposes of this calculation, you would probably assume that the switch closes instantaneously. So there's no time to actually turn on the switch. And then, say you're turning on your PMOS, well, then you just have another path with this R and this C. And so you would add that additional RC to get the delay to the end node. We could call it, Y or whatever you like. But you have to consider it in two stages because each logic gate stops all of the current flowing before it and then starts pulling new current from the supply, right? All right. That's mainly all that I wanted to say about wires today. So you'll recall from last lecture that wires contribute to delay, as we just saw. Especially in modern technology, wires are a big problem and a big contributor to delay. Digital designers often spend more sweat about wire delay than about gate delay because logic gates are still getting a little better with every process node, whereas wires are really not. And we can use this RC model to capture wire delay pretty well. It's not perfect, it's an approximation. The very advanced EDA tools will actually use a more sophisticated delay model for wires, but for hand calculations and getting a rough estimate, this works perfectly well. So actually, there is one more thing about wires. I'd like folks to take a look at this little brain teaser. Read it over and turn to your neighbor or partner and discuss whether you think delay would increase or decrease. Okay, go ahead and discuss. Let's take 3 minutes.
So, I'll let you say.
All right, if you and your partner have come to an agreement, please go ahead and vote. Again, we're using that same poll everywhere link. All right, I see the votes coming in. Let's take 30 more seconds. I know there are more than 20 of you sitting here. All right, let's take a look. We need to come up with a punishment for not voting because we only got 22 votes. I'll think about that for next time. It looks like majority of folks are saying that the delay would decrease if you split up that wire. Interesting. Does someone want to give an argument for why the delay would decrease? Or is that wrong? Does someone want to give an argument for why it would increase, which is the next most popular option? Some of you are right. Any thoughts? Yes. Yeah, so, and remember your name? Okay, yeah, so Brendan's pointing out that if you add more inverters, you're loading up the path with more extra input capacitance associated with each inverter, right? So that's true. Can we get an argument from the other side? Which should be most of you, if I can read the graph right. Does anyone want to argue why it would decrease? Yeah.
So, if we assume that the inverters are really good, then the moment the input voltage is just above the 50% mark, the output is going to bang to the other side.
Mm.
And so if you imagine, with no inverters in between, it's like this wave of, electrons moving slowly, bringing the whole thing up from low to high as it goes along. But with an inverter, as soon as that wave just kind of gets halfway up, hitting the next inverter, that one's going to immediately start outputting rill to the other direction. And so you save some extra delay that it would take to go 51% all the way up to like 10 seconds.
Okay, so we can think about trying to reason based on the sharper transition times from the added inverters, which is a good, useful intuition. And so we kind of have effects going in both directions, perhaps. Let's try to do a little bit of analysis to convince ourselves one way or the other. So if this top wire length, right? We can draw out our pi model, but we don't need to. All we care about really is the resistance and capacitance. Let's say it has some resistance R and some capacitance C. Okay. So if that's the case, we know those are both proportional to length, right? So what's the resistance and capacitance of each one of these segments? And we'll for the concrete example, we'll set n equal to 4 as drawn in the example. So each segment would have resistance of R over 4 and C of C over 4, right? We've cut it up into 4 pieces. Okay. Yeah. Question so far, I haven't said anything radical. I'm just saying that resistance and capacitance both scale with the length of the wire, right? So now let's think about the time constants for the two different versions, right? So the long version has RC. The short version has, well, what does it have? R over 4 times C over 4, right? RC over 16. Notice that there's this squaring effect, right? As the wire gets longer, the delay increases not linearly, but quadratically, because both R and C are getting worse. And so, of course, we don't want to just compare one segment. We want to compare 4 segments. So we need to compare 4 tau short versus tau long. But 4 tau short is still considerably less than tau long, right? And so the point about adding more capacitance as you're adding these additional buffers is absolutely correct. But in this assumption, we basically said ignore inverter delay, right? So that's pretends that inverter capacitance and resistance is very small compared to that of the wire. So given that assumption, those who said that delay would decrease were correct. And it's because of this, at an analytical level anyway, it's because of this sort of fundamental property that delay grows with the square of wire length. So we don't like to have really long wires. Yes. Yeah. So in this example, we assume that that's very small and we ignore it. But you're absolutely right that eventually, if we start cramming in more and more inverters, if we divide it into like 100 very short segments, then that's going to come to dominate the delay. And so, in fact, and you may look out for an analysis problem of this kind somewhere in the future, who knows? But you will find that there is an optimal number of buffers for any given wire segment. There's an optimal length of wire paired with a buffer for a given process, where you balance the added delay from the inverter versus the shortens delay from cutting the wire into multiple pieces. So this is sort of a classic analysis or optimization problem about wire segments, is how frequently to buffer them. And for any given process technology and standard cell design, there's a single optimum length, 100 microns or 200 microns at which you want to insert buffers. And if for those of you in ASIC lab, if you look in your place and routed design and you find a long wire, you will see buffers inserted every so often so that wire can traverse long distances. Okay, any other questions about wires before we move on? So our next topic is probably my favorite one in the whole course. This is what I spend a lot of my regular workday thinking about and sweating about, is energy and power. So we're going to leave wire delay behind, and we're going to move on to this new topic. We haven't talked about energy or power much yet. So far, we've been really first of all, we were focused on functionality, right? And then for the last several lectures, we've been laser focused on delay, on making it fast. We've looked at, how to optimize logical effort in order to find the fastest path through inverters or complex gates. We talked about fan out of 4 as this useful metric, rule of thumb for how to size things to optimize the delay. We haven't talked about power or area so much. Area is relatively straightforward, right? Make gates bigger or have more of them, you cost more area. Vice versa, you save area. Power is a little more subtle, and we're going to talk about that today because in modern systems, especially, power is a super important constraint. So why is that? Why do we care about power? For a long time, digital designers actually didn't care that much about power. It wasn't really much of a design consideration. People didn't spend time optimizing it, right? If we think about back in the 80s or the 90s, there were no smartphones. You had your desktop running Windows 95. It was plugged into the wall. You kind of had as much power coming out as you needed. It just wasn't a big concern. So why did it start to matter? Even before smartphones came around, people realized that trends were heading in a bad direction. So there was this famous keynote talk at ISSCC 2001, where Pat Gelsinger, who was at the time the CEO of Intel, showed this plot. So on the x-axis is time in years, and on the y-axis is power density measured in watts per centimeter squared, right? So for a given square centimeter of chip, how much power was it consuming? And you can see for a long time, it wasn't that much of a problem. It wasn't really increasing. But then starting in the 90s, there started to be this steady and somewhat terrifying rise in power density. And so Mr. Gelsinger pointed out that if scaling continues at the present pace, by 2005, high-speed processors would have the power density of a nuclear reactor. By 2010, a rocket nozzle, and by 2015, the surface of the sun. Obviously not something that you can have sitting in your pocket or even in your desktop computer or really any place anywhere near humans might be, right? So this didn't happen, as you will not be surprised to learn. But it meant that in the late 90s and early 2000s, digital designers suddenly started having to take power really seriously. So we're going to talk about some of that today. We're going to talk about how you analyze it and how you optimize it. First of all, I want to kind of tease out a distinction that may seem simple, but often trips folks up when they're thinking about digital circuits. So we need to think about power versus energy. These are obviously related concepts, but they're distinct, and there are different situations where you want to be thinking about each one. As you hopefully will recall from your high school physics courses or courses here, power is just energy over time, right? So in this cartoon plot, on the right of power versus time, you can see we have this sort of power waveform where power changes over time like this. You can look at an instantaneous power at any given point in time. You can look at an average power averaged over some longer time scale. And then the energy, if we think about kind of the calculus approach to this, the calculus definition, energy is area under the power curve, right? Because energy is power integrated over time, power summed up over time. So we care about these both, but we care about them for different reasons and in different situations. Power in watts is really important for thermals and for cooling. Chip designers will have this concept of TDP, thermal design power. So those of you that are familiar with GPUs for gaming, for example, you might have come across this term. You might buy a GPU. It has a TDP of 500 watts, which is saying that's the maximum power at which it's designed to run in the long term. And so when you're kitting out your power supply, you need to make sure it can feed that much power. And you need to design the thermals or the cooling to be able to dissipate that much power being turned into heat. So power is super important for temperature. And we have this concept of TDP. Energy is, again, just the integral of power, but we measure it instead per unit of work, not in a steady state over time. So you might talk about, it needs to be, joules per something, nanojoules per something. So for example, in your RISC-V processor, you could think of each instruction costing a certain number of joules or nanojoules to execute. Energy is super important for battery life, right? Because your battery in your cell phone has a fixed number of joules, or actually it's often measured in kilowatt hours, which is a confusing unit, but just keep in mind that it's a unit of energy. And it's important in data centers for electricity cost, because data center operators are charged, not by the kilowatt or the megawatt, but by the kilowatt hour. Right? You're charged per unit of energy. You're charged per how many charged electrons you use up and discharge. And most importantly, as we'll see in a moment, energy turns out to directly translate into performance in a power constrained system. And so this is the main reason that starting about 20 years ago, people suddenly became super concerned with power and with energy, is not just because of the power density reasons, but because you can't get more performance without improving your energy efficiency. Let me show you what I mean with an example. So in this example, a GPU has a TDP, a thermal design power of 800 watts. It has a peak deep learning throughput of 1,000 TOPS. So TOPS are tera operations per second. That's just a measure of performance. And then we're told that it has an energy efficiency of 1 picojoule per op. Right? So that's saying that each unit of work is costing a certain amount of energy. What deep learning throughput can it sustain while remaining within this power budget? So this is the kind of problem statement that modern digital designers, particularly GPU designers, but really anyone building a chip is thinking about. So let's go ahead and work out this analysis, right? We have 800 watts. Watts are just joules, joules per second. And then we're told that we have a energy efficiency of 1 picojoule per op. Picojoule is 10 to the minus 12, if you'll recall your SI prefixes. Joule per op. So we'll divide those two terms. And sorry, I think I have a typo in my notes here, so let me make sure I don't mess it up. Yeah, sorry. Let me start over in a clearer way. I apologize. Oh. Mhm. Ugh. Oops. Okay. We'll recover our PowerPoint here and we will begin that explanation again. I apologize. Okay. So we have 800 watts. One picojoule per op. And so if you work this out, it works out to 1250 times 10 to the 12th ops per second. Oh, I'm sorry. Yeah, try that again. 800 times 10 to the 12th ops per second, right? Thank you. Sorry. And so 10 to the 12th is tera ops tops. So we get 800 tops. So this is saying that in 800 watts, we can only fit 800 tops of compute in this energy efficiency. So you note that this is only 80% of peak, right? So what is this saying? This is saying that we've put down 1,000 tops worth of math, but we can't actually turn it all on at the same time while still staying in our power budget. So this design is thermally constrained. It's power constrained. And the only way to improve performance in this power budget of 800 watts is to improve the energy efficiency. So what if the energy efficiency is improved by 20%? Well, now we have 800 joules per second. Our energy efficiency is better, which means it's lower, right? So now we have, let's see, that would be 0.8 picojoules or 800 femtojoules, if you'd like. 10 to the minus 15. And so now this works out as 1,000 ops per second, which is 1,000 tops. Okay, sorry if the explanation was a little garbled there. But the point to draw from this analysis is that given a power budget, given a thermal limit, if you're hitting that limit, the only way to improve your performance is to improve your energy efficiency. And so the only way to improve your energy efficiency, you actually have to go down at the digital circuit level and improve how much energy is being consumed by your circuits for each unit of work. So next, we're going to see exactly how to go do that. But are there any questions about this example or about any energy versus power before we move on? Yeah.
Just 18% change.
Sorry, can you repeat a little louder your question? Mm-hmm. Yeah, so we said energy efficiency is improved by 20%. So I'm saying that our picojoules per op, which is the energy efficiency, decreases by 20%. So it goes from 1 picojoule per op to 0.8 picojoules per op, which I've written here as 800 times 10 to the minus 15. That is equivalent. Okay. Let's talk now about what the implications of this are at the circuit level. So we're going to get back into individual gates and transistors and think about where that power consumption comes from and how to minimize it. We're going to talk about 3 different parts of power consumption in CMOS. The first and most important one is dynamic power consumption. That's where we'll spend the most time. The second is called short circuit currents. And the third is leakage or static power. So we'll take each of those in turn. Let's talk about how much energy is consumed when we toggle an inverter. Sometimes in this class so far, we've been a little hand-wavy or fuzzy with our derivations, but I'm actually going to go through the derivation of this in detail because it's fairly straightforward. And I think it's actually pretty illuminating to understand where the power is coming from and where it's consumed in the circuit. So everyone will recall that we can model our inverter as a simple RC circuit. So let's look at the case first where the input is switching from 1 to 0 and the output is switching from 0 to 1, right? And let's hand wave away the different sources of capacitance, parasitic and load capacitance. Let's just call the capacitance C. And we'll call this resistance, the P resistance R. Okay, we know that the resistance is really going to be the same for N and P in our well-designed inverter anyway. So to derive the energy consumption of inverter, we need 3 facts. Hopefully none of these facts will be particularly controversial. So first of all, you recall from high school physics that power is equal to voltage times current. Second, to formalize what I said earlier about power versus energy, we know that energy is the integral of power over time. And finally, we need to recall the transfer function of a capacitor, the voltage current relationship of a capacitor, which is that I is equal to C dV dt. Hopefully this is bringing some bells from your prior coursework in physics or electrical engineering. Okay, so question 1. We've switched off our inverter, or I'm sorry, we've toggled our input from 1 to 0, which means that current is going to be flowing from VDD and charging that capacitor. And so our question is, how much energy is actually consumed from VDD, from that supply, when we're charging the capacitor? Well, energy is just the integral of power. And power is voltage times current. We know the voltage is VDD. We can rewrite this using the capacitor IV relation. and pull out the constants. Okay. We did a little U substitution there, right? You can abstract this as canceling out the dt terms if you like. So now we just need to know the integral as time goes to infinity of dv, right? And well, we know that eventually the capacitor will charge up to VDD. And so this just works out to C VDD squared. It's the total amount of energy discharged from the supply. With me so far? Bet you weren't expecting me to throw some calculus at you, but so far so good. Okay, next question. How much energy is actually stored on the capacitor when the inverter switches? Okay, we'll start in the same place. Energy is the integral of power. Power is voltage times current, except now the voltage we're concerned about is the voltage on the capacitor, which means it's not fixed at VDD, it's varying over time. So our analysis is going to look slightly different. C dV dt. We'll again pull out the constants. Oops. Sorry, this should be VDD here. And same, I realized I made an error up there when I did the U substitution. All right. Okay, and so what's the integral of V dV? Anyone want to turn on your calculus brain today? Yeah. Right, it's 1/2 V squared. Okay, so that's interesting. We worked out the analysis and we found two different numbers. One number is saying what's the energy consumed from the supply, VDD, when the inverter switches. The second analysis is saying what's the energy stored on the capacitor after the inverter has finished switching. And they don't match. So let's think about what that means. So when the input switches from 1 to 0, we're charging the capacitor. We said the energy from the supply is CVDD squared. Stored on the capacitor is half of that. So what happened to the other half? Well, it went through the resistor and it was discharged as heat. Is used up. So half the energy got stored on the capacitor, and then half of it was burned up in the resistor. It's converted to heat. Yes.
So in the previous slide, how did you go from 0 to VDD of EMT squared times dV to 1/2 CVD? How did you do that interval from 0 to VDD or VT?
Yeah, so recall from calculus that the integral of x dx is just 1/2 x squared.
Oh.
Yeah, so it's just exactly that. Yeah, sort of the kind of the very first integral that you might learn in your calculus course. So now let's think about what happens when we transition the other way, right? We transition the input from 0 to 1, the output goes from 1 to 0. How much energy does that pull from VDD? Well, none additional. Right? Because in this case, the PMOS is not on, so that we're not pulling any more electrons from the supply. After this transition, there's no more electrons stored on the capacitor because they've all been discharged to ground. And so again, this last 1/2 CVDD squared that was stored on the capacitor is used up in the NMOS. So that's where the energy, that's where the energy is going in our inverter transitions. Right? We burn up half of it in the PMOS, we store it on the capacitor for a little while, and then we burn up the other half in the NMOS, and it's gone. Seems kind of wasteful, really. The way to view CMOS circuits from a power perspective is that your digital design is a giant space heater. And it has this useful byproduct that it does some computation for us, right? That every gate is actually is calculating the logic function that it was designed to do. But from an energy and power perspective, we're just burning up energy and converting it to heat in the transistors as each gate toggles. And so in order to optimize this, we need to think about how can we use that energy conversion into heat as judiciously as possible and waste as little as possible in order to get the computation done. So let's think now about the energy per transition of this inverter. Let's sum up what we just talked about. Right, where a transition is a full cycle from 0 to 1 and then back to 0, right? So it's the capacitance you're discharging times VDD squared. And so if we think about power is energy per transition times transitions per cycle times cycles per second. Well, we just said energy per transition is CVDD squared. Cycles per second is just our clock frequency, which we'll label as F. And so then we have this question of how many transitions in a cycle. And so we're going to define a constant there called alpha. Alpha is what we refer to as the activity factor. And this is a really key determinant of power in our digital circuits. So a clock, which toggles from 0 to 1 and then 1 to 0 every cycle, has the largest possible activity factor, which is 1. But it turns out that most gate inputs and outputs do not toggle most cycles. So a typical alpha is something like 0.1. Because most of the time your inverter or your NAND gate or your NOR gate, for whatever reason, is not going to toggle every cycle because its inputs didn't happen to change that time. So this is the sort of classic definition of power in a digital system. C VDD squared times alpha times F. For energy, or at least energy per cycle, you just drop the frequency term, right? So let me make a note of that here explicitly. So energy is just alpha C VDD squared, right? Because we don't care about cycles per second in order to determine energy per cycle. Okay, questions about energy and power so far? Yes. Yeah, so activity factor, the question is, why does activity factor depend on gates and data pattern? So it depends on the inputs to your circuit, right? Let's say you're on your FPGA, you've designed a circuit that will increment a counter every time a user pushes a button on your FPGA board, right? If the user isn't pushing the button, then your activity factor is going to be 0. None of your inputs are toggling. It's also the case that many gates have this nice property that they mask transitions, right? So think about an AND gate. If both of the inputs are 0, and in a given cycle, one of the inputs toggles from 0 to 1, the output of that AND gate is not going to change. It's going to stay as 0. And so therefore, the load capacitance that the AND gate is driving never toggles. So it depends both on your inputs and on the gates, the logic functions that are laid down as to what your alpha actually is. And in practice, to derive alpha, what we typically do is we simulate some real workload of interest on our digital system, and then just go count for every node, how many times did it toggle, and average that out to get the alpha per cycle. So alpha is not universal for a whole design. It's going to be different for every node in your system. Yes. Yeah, in these analyses, we roll all the capacitances, parasitic and wire, if you like, into this total CL, because for the purposes of energy, we don't care what capacitance we're charging. We just care how much in total we are. Okay. Now that we understand where dynamic power consumption comes from, let's talk briefly about how we can optimize for it. So one option for reducing dynamic power consumption is to play with the voltage and the frequency knobs, right? In particular, you notice that power and energy both scale with VDD squared. So reducing voltage is a very powerful lever to save energy. Reducing voltage also reduces your performance. It reduces your frequency. So this is a classic trade-off between power and performance by using the voltage setting of your circuits as a knob. You'll notice that this cartoon is showing something called DVS, also called DVFS, dynamic voltage and frequency scaling. So many modern digital circuits will have the ability to adjust their voltage dynamically depending on the program behavior. So in a workload phase where you need a lot of performance, you can increase the voltage to spend more power, spend more energy, but improve your performance. And then if you're in a lighter workload phase, you can decrease your voltage to operate in a more energy efficient regime. The other knob that we have, or a second knob that we have, is to reduce the capacitance. That's CL, right? Yeah, 1 second. So you can reduce capacitance by making gates smaller. In all of the previous examples, we looked at how making gates bigger tends to make them faster, right? So that's another design time performance power trade-off, where smaller gates will have less capacitance to drive and will consume less energy. Long wires can be shortened in order to reduce the capacitance of those wires. And then lastly, we can try to reduce activity. A common way that this is done is through something called clock gating. A sort of toy clock gate circuit is shown on the right here. Clock gating is basically saying, if we know that a flip-flop is not going to update its value that cycle, then we'll shut off the clock so that the clock will never even reach that flip-flop. So that's one way to reduce the activity factor. It's adding more logic. It's spending area in order to reduce the activity factor of the gates downstream. So these are some common optimization techniques to mitigate dynamic power consumption in digital circuits. Okay, yes, question. Yeah, good question. We won't talk about that in detail today, but you can refer back to your transistor models that we talked about at the very start of the delay section. Recall that we have these I-V curves, right? And in general, if you push V out on the curve, your current increases. So higher voltages, higher gate voltage and drain voltage, drain to source voltage, means that your current is higher, which means the effective resistance is lower. And so that makes each gate faster. We didn't talk, yeah, you're correct that we didn't talk a lot about voltage supply and that as a knob to adjust delay during the delay analysis that we did. But in general, it's definitely the case that higher voltages make the transistors stronger. It means they can drive more current. It means the effective resistance is lower. Okay, any other questions about dynamic power consumption? Okay, let's take a little break. I am curious to hear your thoughts about this one. So please go ahead and respond. It's totally anonymous. Remember, you're not going to get in trouble. I'm just curious. And it should be set up so that you can vote for more than one option if you feel like more than one apply to you. Yeah.
Like previously, we would configure the gate.
Yeah. Not universally. Yeah, we talked about how there's a trade-off. We did the but generally larger gate will have stronger drives. They'll be able to drive the next stage faster. You'll see some scenarios where making gates smaller will make them a little slower, but will kill a lot of them.
Well, some of us couldn't do that. Some of us pulled all night on the flat boy.
So that perfectly realize perform the logical effort analysis. Right? So we talked about how specific gates, any gate topology, we're trying to figure out how much worse of a driver it is compared to the curve. Right. The point of that is you want to have your N and your P networks balanced. If you have device.
Yeah, this stuff is just like understanding the
Yeah, I use this.
I think that was just in preparation. Okay, cool. We got a lot of responses. Let's talk about this one. So it looks like most folks are using these tools. Okay, well, I'll turn the problem off so we can talk about it. Yeah, I mean, I guess I'm curious, does anyone want to share your experience, like how helpful are these tools, I guess, is one thing that we're wondering. I think it doesn't make sense to like assume that or it doesn't make sense from our perspective to try and ban their use, right? Because that's not realistic about what your future schooling and your work experience will be like. Yeah.
I think at like the very beginnings, because of how different Verilog is from like the languages we're used to.
Yeah.
I think like the debugging thing is like pretty helpful because even if the debugging message is good, it still might not make any sense to you since you've like just been exposed to it.
Makes sense. Other thoughts? Yeah. Yeah, that is something to be careful about, I guess. We've we've definitely had we have seen students who try to get a lab checked off, and it was clearly written completely by an LLM, and it just did some very nonsensical or wrong things. I think in general, they are way worse at Verilog than at Python, right? So you do have to be pretty careful in how you're using them. But yeah, I think it makes a lot of sense to try to make an error message more intelligible or to ask conceptual questions. Our main hope is that you don't use it to turn off your brain, right? Because the whole point of this class is for you to use your brain so your brain will get stronger. And if the LLMs are helping you with that, then that's great. If the LLMs become a shortcut so you don't have to, you can try to do the work without turning on your brain, then you're not setting yourself up for success later in life when you will need that brain in order to be successful. Cool. Thanks for sharing about this. I think this other course staff will also be interested to see people's thoughts. Okay, let's talk briefly about, let's see, where were we? Here we go. Let's talk briefly about the other sources of power. Why is this not showing up? Okay. Okay. Let's have a word with the folks at Microsoft here. Okay, sorry about this. PowerPoint is very grumpy. What if I do the presenter view? No. Okay, let's give it one more try. Okay, we're back. Sorry about that. Let's talk briefly about the other two sources of power consumption that we mentioned earlier in the lecture. We talked about this. Source number two is short circuit current. This is another source of power consumption that happens when gates are switching. And this comes because of a sort of imperfection in how we designed and set up our CMOS gates, right? One of the really nice properties of CMOS is that you always have either the pull-up network, PMOS, or pull-down network, NMOS, on, but you never have them on at the same time, right? So you're either charging up that capacitor and then you're done, or you're discharging that capacitor and you're done. However, there's an exception to this, which is what about when the input is halfway through switching, right? It's right in the middle of that voltage region. You know, say the input is VDD over 2, when the input transition is halfway between 0 and 1, or 1 and 0. Well, in that case, it may just be the case that the input voltage of both your NMOS and your PMOS is exceeding the threshold. And so there's going to be a brief time where your pull-up network and pull-down network are both on, right? So this is also related to switching activity because it only happens when you have a transition. It's typically a relatively small effect compared to the actual primary source of dynamic power consumption of charging or discharging that output capacitance node. But you can see this, the waveform here. And this would be in a much older process with like a VDD of 0.5 or something like that. Whereas as you transition the input voltage, you get this sort of transient current flowing through your NMOS, your PMOS and your NMOS together from VDD directly to ground. So this is the short circuit current. We typically don't worry about it that much. Why is that? Well, threshold voltages, recall that we need to exceed the threshold voltage of the transistor to turn it on. Threshold voltages do not scale as fast as supply voltage. And so over time, as VDD has been getting smaller and smaller, threshold has been mostly staying the same. So typical threshold voltages are around, I don't know, 300 millivolts or 400 millivolts. As typical VDD has decreased from 1.2 to 1 volt to 0.8 to 0.6, the amount of time that both the PMOS and NMOS are exceeding their threshold and turning on those transistors is getting smaller and smaller. And so in modern technology nodes, this is becoming less important of an effect. We don't worry about it as much. The one exception is if you have very slow transitions, right? So if you have a very weak driver, like we were sort of talking about with the long wire example earlier, you might have a very slow transition from 0 to 1 or 1 to 0, in which case you might be spending a lot of time in that undesired middle region. You might have a lot of short circuit current. So typically we try to size our gates and avoid long wires to avoid those very slow transitions. Okay, lastly, we have this concept of leakage or static power. So this is yet another of the abstraction levels of CMOS that we need to peel back and look under the hood a little bit, right? Previously, we've modeled transistors as switches. We said they're either off or they're on. But unfortunately, especially modern transistors, when they're off, they're not really off. So that's a bummer, right? We get this leakage effect. So we had previously this VGS IDS curve. In the region where the transistor's on, we had this sort of linear regime. But then if you look at this off region, it's not actually quite 0. And so if we zoom in on this region, and in particular, we'll put the y-axis on a log scale now, so we can look more carefully what's going on. The current never actually goes to 0. It just drops off exponentially, according to this fairly complicated looking equation on the right. You don't need to worry about the details of that. The key is just that there's this exponential relation at sub-threshold voltages where current gets smaller and smaller, but it never turns off. So even when our input voltage to a transistor, an NMOS transistor, is 0, if there's a voltage difference between source and drain, there's still going to be some very small amount of electrons flowing from source to drain. And that's our leakage current. So we can't do that much about leakage. It's always there. One thing we can do is called power gating. So power gating says if a whole block is not in use, shut off the entire supply to that block, right? If all three terminals of the transistor are the same voltage, then there's no leakage, right? Because there's no voltage differential anywhere. The other thing we can do is try to adjust this threshold voltage. In particular, if we adjust it to the right, if we set the threshold voltage to be larger, right, you can see how that's going to more firmly shut off the transistor by the time this curve gets to 0, right? Because the curve of a high VT cell might look something like this. So that helps our leakage if we set voltage higher. But you also notice that when the transistor's on, the current is now less. So high VT devices reduce leakage power, but they also hurt the delay. They hurt the performance. And so this is yet another performance power trade-off. In a typical CMOS process, you'll have multiple families of transistors to choose from and gates designed from those transistors. So for any given inverter, in addition to its sizing, you can decide whether to use a high VT inverter or a regular VT inverter or a low VT inverter. Typically, there's multiple, at least 3 or 4 different families of these threshold voltages, which are set based on different amounts of doping in the silicon process. Okay, any questions about these last 2 sources of power, short circuit or static power? All right, we're almost out of time, so let's wrap it up there for today. Next time, we're going to look at one more example with power, and then we're going to start talking about arithmetic. Hello.
Question?
Yes.
Like, orderly?
Yeah.
I've seen different definitions where you take the half of the resistance, so it's basically sum of the resistors.
Yeah.
And then you multiply that by the classical.
Summing the resistances and summing the capacities. Yeah, you can define it either way. You get approximations that are you get one approximation is more accurate in some circumstances and one is more accurate in other circumstances.
Yeah, so in this example, I got like 7 RC.
Right.
Which one would be more accurate?
I guess you'd have to look at the details of the inverter sizing and the wire layouts and stuff to figure out what your ground truth is to compare to. So for the purposes of this class, we'll just use the downstream capacitance definition,
Right.
I guess. But you're absolutely right that you can use both approximations and they may be more useful different.
Right.
Yeah, that's a good point.
Cool. So if I use like the other